Okay, guys, here we are with section 2, which is manipulating KEQ. If you think back to the thermodynamics and the electrochemistry unit, we've got all sorts of things where we are going to find ourselves in a situation where we're going to have to, for example, flip an equation backwards. All right, happens all the time. Or we're going to have to take an equation and multiply it by 2, or cut it in half, or add some equations together, right? So all the Hess's law stuff that we did back in the day, we're probably going to have to do again. The only difference is that there's going to be a different set of rules when we are dealing with KEQ because of the structure that we put into place and because of the ground rules that we established for KEQ. So some of the things are going to be similar to what we did in the past, and some of the things are going to be very, very different than what we did in the past, and you got to make sure that you are playing with the right set of rules. So the first thing that we're going to look at here is what happens when we reverse an equation. So let's examine this equation right here. So can you tell that we have 2 hydrogens and an oxygen going to 2 waters? And the 2 hydrogens and the oxygen are on the left. But in our bottom equation here, the 2 hydrogens and the oxygen are on the right. We have flipified them. And then what you've got is you've got the water that is here, and the water is on the right-hand side to begin with, and it's on the left-hand side over here. So all we've done is we have reversified it. So please note that in the forward reaction, because the waters are on the right-hand side, they are up top, and again, properly squared because there's a 2 there. And then over here, you've got the hydrogens and the oxygen that's on the left. So here's the oxygen and the hydrogen on the bottom of the equation, again, properly squared and squared here, and to the first power and to the first power for this guy because of that, right? So basically what we've got here is we have got the red products over here and the green reactants over here like so. But now what we're going to do is we're going to flip it. And when we flip it, those all go over to the other side, and these all go over here. So not surprisingly, the red water ends up on the bottom, and the green hydrogen and oxygen ends up on the top over here because we have reversed it. So in a normal situation, back with electrochemistry and thermodynamics, when we changed the direction of the equation, all we had to do was slap a negative sign in front of it. Now you don't do that. There's no negative sign involved. The only negative sign that's involved is in the exponent, because what you are doing is you are changing it from products to reactants and reactants to products, which means the numerator goes to the denominator goes to the numerator. And so what you are doing is this, that K of the forward reaction is going to be equal to K of the reverse reaction inverted. So if you have to flip an equation, you now no longer put a negative sign, you invert your K value in order to keep pace with the mathematics of everything. So let's look at an example. So here is an example. And for our example, what we have here is we have A plus B goes to C, and the value is 1.2 times 10 to the negative fifth. But let's say I don't want that. Let's say that instead of that, I want it to be the reverse of that. So I have flipped it. So the C is now on the left and the A and the B are now on the right over there. So if I flip this equation, in the olden days, I would just call this negative 1.2 times 10 to the negative fifth, but that's wrong. That is using wrong mathematical logic for this. I don't flip it, I invert it. So I do 1 over 1.2 times 10 to the negative fifth, or 1.2 times 10 to the negative fifth to the negative 1 here, and I end up with a value of 8.3 times 10 to the negative fourth, assuming my math is correct. So when you flip an equation in equilibrium, you do not take the negative sign of it. What you instead do is you invert it, or you take it to the power of negative 1. So check this guy out. So for this guy, you've got hydrogen and bromine on the left and hydrogen bromide on the right, and your Kp is 5.6 times 10 to the 6th here. If you instead flip it, so all I have done is taken this equation and I have reversed it. Again, I do not take the negative of it. What I instead do is I take the inverse of this. I take 1 divided by, or 5.6 times 10 to the 6th to the negative 1. and plug that into your calculator, and you get a value of 1.8 times 10 to the negative 7th that's there. A couple things to note here is that apparently this equation is extremely product favored. How do I know that it is a product favored reaction? Because look at the size of this number. It is a very large number. So it likes to be on this side over here. It likes the HBr. Now, if I flip the equation around, it's still going to like to be with the HBr. But the HBr is now on the left-hand side. And so what happens is when I invert this number and take the reciprocal of it, I end up with a number that is very small, and it is a reactant-favored reaction now, which makes sense because it likes the HBr, but since the HBr is now a reactant, we're going to need a very small number to represent that. So by changing the way that we view the reaction, it doesn't actually change anything, except that it changes the overall way it looks, and the mathematics then have to follow suit along with that. So rule number one is that K forward and K reverse are inverted from each other. If you flip an equation around, you have to invert or take the reciprocal of that value. All right, well, what happens if we change the stoichiometry? Sometimes in order to get the equation that we want, we don't want the stoichiometry that's given to us. Well, let's take a look at this example. I've got water here with a 1 in front, and it's a reactant, so it's on the bottom down here. And then I have these guys here, which are products, a 1 and a 1/2. So there they are, 1 and a 1/2, with, again, the water being down below. But let's say I don't want that half. Oh, that half is bugging me for whatever reason. And so I want to get rid of that 1/2, and I want to multiply this whole shooting match by 2. So if I do so, that would then be a 2, that would then be a 2, and that would then be a 1. Well, what would then change as far as the equation is concerned? Well, instead of this guy here being a 1, he would now be a 2, and so he would get a squared. So what we have done is we have taken the 1 that was there, and we've put a 2 in, so we've squared it. This guy here was a 1/2 that was there, and now instead of being a 1/2, he's a 1. Well, what has happened? Well, I've doubled it, and so because I have doubled it, I have essentially squared it. What's the square of a square root? The square of a square root is just the 1 that is listed there. And similarly, what about this guy? He started off as a 1 because there was a 1 there, but now that there's a 2 there, I'm going to end up squaring it because I'm going to need to incorporate that 2 that is there. So your basic rule is very simple. Your K new is going to be the same thing as your K old, except it's going to be raised to that power. Now, think back to thermodynamics. What did you do in thermodynamics when you doubled an equation? When you doubled an equation in thermodynamics, you simply multiplied it by 2, right? Well, shouldn't that just stay for everything? No, because remember in electrochemistry, what happens in electrochemistry when you double an equation? You don't do anything. So again, every set of circumstances has its own rules. So in equilibrium, when you double equation, you have to square it. In electrochemistry, when you double equation, you do nothing. In thermodynamics, when you double equation, you have to multiply it by 2. So all of these are slightly different rules based upon the mathematical constructs that we have created for these guys. So let's look at a couple of examples that is here. So in this example, I have a 1/2 and a 1/2 and a 1, and my value is 4.3 times 10 to the negative 2. But let's say I want to take this whole thing and multiply it by 2. So 2, 2, and 2. So 2 and a 1/2 is now my 1, 2 and a 1/2 is now my 1, and 2 at 1 is now my 2. So I have doubled this equation. If I want to figure out what my new K value is, all I have to do is take the old K value, which is here, and then raise it to the power of the stoichiometric coefficient that I applied to the balanced equation. So because I doubled all of these equations here to get to this one, I'm going to end up squaring my K value, and now that's going to be my new K value to incorporate all the different changes that I just made. All right, let's take a look at this one here. So in this one here, I've got a 1, 6, and a 4, and this is my particular value. Let's say that I want this to be the 1. So what am I doing? I'm dividing this whole thing by 4. So this is going from a 4 down to a 1, a 6 down to a 1.5, and a 1 down to a quarter here. So if I am cutting this by a fourth, right, then I'm going to raise this equation here to the 1/4 power. So I'm going to take my normal number here that I started with, and because I divided this whole equation here by 4, or more to the point, I multiplied it by a quarter, I am now going to raise this to the 1/4 power, and I'm going to get my different number that is here. So our second rule is K new is going to be equal to the K old raised to whatever stoichiometric thing that you did. So if you take the old equation and you double it, then you're going to take that K and you're going to square it. If you take your old equation and you triple it, then you're going to raise that to the 3rd power. If you take your old equation and you cut it in half, then you're going to take your old K value and you're going to raise it to the 1/2 power, which is the square root. All right. All right, one more to go. What happens when you add equations together? Well, take a look at what happens when you add these equations together. Here's equation 1, which is solid sulfur plus oxygen goes to sulfur dioxide. Products over reactants raised to their powers, ignoring solids, liquids, and solvents. I get this SO2, which is a gas, as a product. And I get the O2, which is a gas, as a reactant. And please note that I have ignored this for our K equilibrium expression because it's a solid. All right. Now, what happens when I take this guy? Well, SO3 is a gas, so he counts and he goes up there. SO2 is a gas, he counts, he goes down below. And half of an oxygen, he counts, he's a gas, he goes down below. But please note that he is a half because of that. All right? Now, what's going to happen if I add these two equations together? Well, when I add these two equations together, check out what happens. I still keep my sulfur, and then I have an SO2 on the left-hand side, and I have 1.5 oxygens, so that's 3/2 oxygen that's a gas. And that's going to be in equilibrium with an SO2 that's a gas and an SO3 that's a gas, which is here. All right, well, check it out. The SO2 and the SO2 on the left and the right, they cancel each other out. They're gone. So the only thing I'm left with now is the sulfur, that's the solid, which is this guy, and the 3/2 oxygens, which are these guys, and the sulfur trioxide, which is this guy, and then the sulfur dioxide here and here canceled each other out like they normally would. All right? Now, how does that and this get you our new equation here? Well, what would our new equation be? Our new equation is going to be the pressure of the SO3, which is my product, and then I'm going to divide that by the pressure of the oxygen raised to the 3/2 power, because that's this guy. And I am going to ignore the sulfur because he is a solid. He doesn't get to play in this equation that is here. So how then does this equation and this equation give us this equation? Well, all you have to do is multiply them together. So if you take the KP1, which is this guy, oh, there's a lot going on here, but if you take the KP1, which is this guy, the SO2 divided by the O2, and you multiply it by the KP2, which is this guy, all right, specifically this part here, and that's this guy here, that's going to get you the KP3, which is this guy, which is what happens when they all get added in together. So all you have to do is multiply them together. KP1 times KP2 is going to give you KP3, which is what you want. So that is a slightly different variation compared to thermodynamics and electrochemistry. In thermodynamics, if you add two equations together, you simply add them together. In electrochemistry, if you add two equations together, you simply add them together. But in equilibrium, if you add two equations together, you don't add them together, you multiply them together. So the total is going to be K1 times K2 times K3. However many Ks that you have, however many equations that you have to add up together, you are going to multiply them together, and that's going to get you your new K. So when you add an equation, you do not add their K values, you multiply them. So if I take equation 1 and equation 2, and I add them together to get equation 3 down here, and I have K1 and I have K2, in order to get K3, all I have to do is multiply these two guys together. That's what the rule says. Okay, so let's take a look at this guy here. Here's equation 1 right here. Here's equation 2 here, and we want to get equation 3 here. So what are we going to have to do? Well, equation 1 is this, and I want to keep that. And we're then going to keep the C2O4 here. So that looks good. So it looks like all I have to do is add these two equations together. Because if I do, watch what happens. The HC2O4 negative 1 and that guy, they cancel each other out, so they go away. And then the waters add up together here to give me the two waters that I need that are here. And then the H3O positives that are here add up to give me this guy here. So it looks like all I have to do is add this top equation here to this second equation that is here. So if I add up those two equations, then I get the equation that I want. So if I have to add equations together, what do I do with their K values? I simply multiply them together. I do not add them together like I would in thermodynamics. So all I have to do is multiply this by this, which is what this is showing us, and that is my new K value that is there. So if you simply add equations together, you multiply their values. Here's another example. How am I going to take this top equation and this middle equation here and get this third equation down here? Well, let's see. I like the carbon solid for that guy. So it looks like this whole equation here, I'm just going to leave it as it is. I'm not going to change a thing. All right? But it looks like from our second equation here that I have one COCl2, but I need two of them down here. So what's the first thing that I'm going to do? First thing I'm going to do is take this whole equation, I'm going to multiply it by 2. 2, 2, and 2. So that I now have two of those guys, which is what I want. And I also then have two of these guys, which is what I want here, right? But if I double this equation, and I take this whole equation, I do 2, 2, and 2, then I have to correspondingly change my K value. So this is no longer going to be 4 times 10 to the negative 4th. Because I am doubling everything, I now have to square this. So I get out my calculator, and I do 4 times 10 to the negative 4th, and I multiply it by 4 times 10 to the negative 4th. So 4 times 10 to the negative 4th times 4 times 10 to the negative 4th. Okay, I keep pushing buttons wrong on my calculator here. 4 times 10 to the negative 4th times 4 times 10 to the negative 4th. There we go. 1.6 times 10 to the negative 7th. I don't know why that was so hard. So this is now 1.6 times 10 to the negative 7th. All right. So now check it out. Watch what happens. What happens is I get my carbon where I want it. I now have my carbon dioxide where I want it. I now have my chlorines where I want them. And I now have my carbonyl chlorides where I want them. I've got 2 carbon monoxides on the left, which cancels out with 2 carbon monoxides on the right. and I have everything that I need. So if I now add these two equations together, I get the equation that I want. So in doing so, when you add equations together, you do not add their k-values, you multiply their k-values. So it's going to be 2 times 10 to the 13th multiplied by 1.6 times 10 to the negative 7th. So when you add them together, you actually multiply their k-values, and you end up with an overall value of 3.2 times 10 to the 6th that's there. So that is our second rule that we have. Actually, our third rule. So our first rule is reversing equations. Our second rule is changing the stoichiometry. And our third rule is adding equations together. So when you do all that, you now have the tools that are necessary to combine all of them together and do Hess's law problems, but with the mathematics of equilibrium. Now the rest of this sheet is comparing Kc values and Kp values. Back in the day, they made you do this, and so this goes into extended detail of how to compare and contrast Kp and Kc. They have taken that off of the test, so I'm not going to bother to go through any of these examples. The only thing that you should know is that if there are the same number of moles of gas on each side of the equation, then Kp and Kc are the same, and that is going to be a particular subset of a reaction when we start dealing with Le Chatelier's principle, but I'm not going to get into that now. So basically what you need to know is that if you reverse a reaction, you invert it. If you change the stoichiometry, you raise it to that new power. And if you add equations together, you don't add their k-values, you multiply them. These here are probably not going to come up on the test, so I'm not going to waste your time going through those. If you're really interested in learning about those,